Hello, and please welcome you all to our today's in CBK Pan Engineering Seminar. Today's lecturer and guest is Dr. Joanny Siwek from the University of Adama Mickiewicza in Poznań. Dr. Siwek will tell us a little bit about the artificial empathy in a swarm of robots. Well, as you all know, the artificial intelligence is one of the biggest topics in science, but also in media right now. But the fact is that most of the people do not know what real artificial intelligence is. And I'm sure it's even harder to understand what an artificial empathy is and how it can be used in a swarm of robots. So please welcome today's lecturer, Dr. Joanny Siwek. Dr. Joanny Siwek is an assistant professor in the Department of Artificial Intelligence at the Faculty of Mathematics and Computer Science at Adama Mickiewicza University, Poznań. The main focus of her research is the implementation of artificial empathy in learning and adaptation processes. Dr. Siwek employs the concept of theory of mind and cognitive empathy combined with a fuzzy approach to design swarms that not only cooperate but also learn from each other in the same way humans do. She leads the Artificial Empathy in Swarm Research Group, which connects researchers from Adama Mickiewicza University and the University of Technology, Poznań, as well as students and companies interested in the project. In addition to her research, Dr. Siwek manages the computer science program at the faculty. So I'm sure that after today's lecture will also be the persons that would like to help in that in growing that type of knowledge, because it sounds really interesting. So Dr. Siwek, please start today's lecture.
Thank you very much for the introduction. Hello, everyone. I would like to tell you something about my research, but the group that manages this research is actually quite a big group, a big still growing team of both researchers and students. I will try to show my presentation. Okay, can I get some feedback if it's visible?
Yeah. Yes, it is.
Okay, thank you. So slideshow from the beginning. Okay, so the title is Artificial Empathy in a Robot Swarm. And when I'm telling new listeners that I'm dealing with artificial empathy, everybody connects this notion, this term, with emotion. So nowadays there is a growing interest in artificial intelligence, and since it's coming to our houses, everyone has something that has an AI in it. Everybody uses ChatGPT. Everybody knows what AI is, of course. So the problem, the notion of ethical artificial intelligence is getting more and more popular. And also in recent years, this year and the previous year, many grants and funding was given to projects connected with ethical AI and with a branch of research called affective computing. For example, Sony had a very big grant for financing research in artificial empathy. But artificial empathy, it's not really a case connected with emotions. Most of people think that artificial empathy is a branch that wants to make AI more emotional, so it makes AI less psychopath, so more emotional, more connected with people's emotion, better in responding to people's emotion. So in a way that makes it less wrong, I would say, even so, less psychopathic. Because if we have in real life, when we have a psychopath, it's a person that understands the emotions but just don't use it, don't use the emotion, but still can control them and can control emotions in other people, getting some benefits from the said control. But artificial empathy, first maybe empathy. Empathy is a quite new term. It was developed in previous millennium, yeah, but in Germany, but at the end of the millennium, and it is connected with perception. It's connected with prediction of another person's possible actions. So it's the knowledge, it's the ability to get in the shoes of other person and to imagine what the other person can think or can do next in their situation. And artificial empathy is the model's ability to predict that kind of behavior in the empathy target, because we can say that people are empathetic, but also we want to develop empathetic systems or empathetic agents. So it's not always the person that we are trying to take as a target of the empathy. So from the one side, it's understanding emotions, understanding situation, understanding the way of thinking of other empathy targets or people. But on the other side is the possibility of imagining, of predicting, of making some kind of forecast about what will be the next action of the empathy target. And a notion connected with artificial empathy is affective computing. But while artificial empathy allows a system or an inanimate object to be empathetic, so it allows a system to develop empathy. For example, as in empathetic AI, affective computing does not allow this kind of thing. It only reacts. It's reactive to people's emotion. It's more connected with better interaction, human-machine interaction, better data collection and data analysis about the emotion of, for example, customers. So it does not allow an agent that is not a human to be empathetic. And the last notion that is very deeply connected with artificial empathy is cooperation. Because artificial empathy allows for cooperation. We cannot cooperate as humans if we do not know what our cooperative partner can do, what he or she is able to do, or what are their abilities, and how can we choose our own action in order to cooperate to reach some kind of common goal in cooperation. So empathy, artificial empathy, affective computing, and cooperation are connected with each other. The terms are connected with each other, but artificial and empathy that we develop in our system suggests that the system itself can be empathetic and can be both the source of empathy and the target of the empathy. In human life, empathy can be learned. People learn empathy from the very early months of life. The first signs of empathy is 18th month of a child's life. and it's connected with mimicry, with doing the same things, mimicking parents' exaggerated emotions, reactions, some kind of movements. So it's really basic. Then we have in older years we have emotional contagion. It's visible in the situation when, for example, babies in kindergarten start crying, and one starts to cry, and then everyone in the group starts crying. So it's contagious. Then we have emotional empathy. Emotional empathy is connected with emotions, especially with basic emotions like happiness or sadness, but also anger and this kind of basic emotions. Then in the years we have cognitive empathy, and cognitive empathy is connected strictly with learning, and that's the part of the empathy that we want to model, and we use in our robots that I will describe later in the presentation. So cognitive empathy is connected with cause and reaction mechanisms. So it's connected with making connections between the cause and the reaction, with a step of understanding and predicting what the reaction can be. And the highest level of empathy is sympathy and compassion. So the higher emotions, but also the most visible, the upper level of empathy is so-called Schadenfreude, from German. It's the way where it's an emotion when we are happy because somebody else has a problem or something bad happened to somebody else. So it's having our own emotions that stem from understanding other person's state, but are not in the same direction as the emotions that are coming from the empathic target, but are exactly the other way around. So we can distinguish ourselves from the empathy target, and we know that we are a different person, and still we can put ourselves in the shoes of the other person, and we can have our own emotions as a response to other person's emotion. And in the existing systems, in the existing artificial empathy systems, of course, we have systems that can reflect some kind of emotions, that can act based on some emotions that they collect from users. We have systems that mimic some things that people do, and we are trying to create our systems that use cognitive empathy, yet really empathic systems, like the systems that have their own empathy, are not yet created, are not yet possible. But as I will show you in the next slides, the cognitive empathy is now, I would say, well modeled. So we have a mathematical model for cognitive empathy that works. Sorry, that works, and we can actually teach artificial systems. We can teach and inanimate systems to derive the cause reaction mechanism by themselves, and to learn and to teach other robots or systems how to act based on the empathy. Artificial empathy right now has some real life applications, mostly in using data collected from users in order to, for example, make good advertisements or movie trailers. So the kind of taking emotional information from people and implement them in systems that just take data that will make the wanted reaction in the users. So just the systems connected with collecting data, but also we have autonomic vehicles where artificial empathy is used to monitor the state of the driver. We have virtual companions and virtual assistants that are more realistic, more human-like, and implement compassion and implement motivation in order to help people fight depression or to achieve more personalized goals in learning. And we also have computer games. We have NPCs that are more realistic, that respond to the user in a more realistic way, that is connected with the user's game history and is more adequate to the situation that happens. And also we have artificial empathy in robots. In 1990s, there was a boom in artificially empathic robots. There was a university in Osaka where people developed that kind of robots. There were two main attempts. One failed. It was a robot that was created with an endocrinologic system, but it had scenarios of how to act, so it wasn't really effective. And the other research was a robot called Affeto, and the project is still running right now, and the researchers teach the robot how to react to pain, for example, with a facial expression. So they do not script how the robot should act. Just there is a person who acts as a parent of the robot, and the person makes expressions that are exaggerated, and the robot learns how the expressions should look like and mimics it to when feeling the pain. The pain is given to the robot as electrical current. So there are also research in artificially empathetic robots, but when talking about swarms, our project is one that we know about. We looked everywhere, and ours seems to be the first one. Why implement artificial empathy in robots? So first of all, it reflects the human way of learning by the person themselves, so without any external interference. Also, it allows learning from other person or other robots experience. Also, it allows for adaptation and cooperation, actually knowledge actualization. It's more intuitive and corresponds with the actual brain structure, because artificial empathy or empathy in humans has its corresponding neurons in the brain. They are called mirror neurons, and they are placed in the outer layers of the brain. And by medical experiments on people who had some brain damage, we are sure what parts of brain are responsible for the artificial for the empathy. And as I will show in the next slide, and the empathy is also divided in the emotional and learning parts. So that's the basic model, and the model stems from the very brain structure. We divide the empathy into emotional empathy and cognitive empathy. And emotional empathy is more primitive, and it's connected with the primitive responses and with emotions, and it's hard to model. So we do not focus on it in our research. We focus on the cognitive empathy, so on the empathy that is connected with learning, understanding, recognizing intentions, and the ability to predict other or the empathy targets next action. On the market, we can find many different robot swarms. They are all with different modalities. So they are mobile robots, they are flying robots, and there are very many different types of them. One of the most popular are those created by Amazon, and the robots that are more feasible for researchers and even schools are kilobots, but they are a little bit old right now. But none of these robots actually can act in a way that allows for decentralized learning, that allows the swarm to learn how to do particular actions by themselves without any additional data, without any additional scripts, and also without a so-called overhead controller, so additional computer that steers the robots. And the motivation for our research were the works of Huang about a swarm of caribou that were to escape from a wolf. And this research was conducted only simulatively. And in the research, the caribou was to escape from the wolf and just to survive. And the wolf was to eat the caribou. And the applying a very simple empathic parameter of caribou, knowing where the nearest caribou is, nearest other caribou is, and what's the distance between the caribou and the wolf. The caribou were able to develop more effective strategies of escaping the wolf. So having this kind of motivation, first of our research was in the time of COVID. We came up with our own idea of the so-called antibody problem. So the problem of a swarm of antibodies that are to surround a virus, and deactivate the virus. So the idea was for the antibodies to cooperate, to signal, to gather in groups of 5, and to surround the virus and to deactivate the whole every virus that was visible. Our research problem that we are trying to solve is if the use of artificial empathy algorithm actually has an added value. So if it allows for faster or more effective achievement of a global goal in comparison to the normal swarm, so a swarm of agents that cooperate but do not cooperate in an empathic way. And we are trying to prove with some success that using this kind of empathic algorithms actually help to achieve the global goal in some few seconds faster than in a normal way in the comparison group. So that's our team. We have people from Poznań University of Technology and from Faculty of Mathematics and Computer Science from Adama Mickiewicza University. We have both professors, assistant professors, so we also have students, and we have bachelor students, and we have master students. So the group, some of the students come, some of the students go, because we have some kind of projects that students help us with, but everybody brings their own added value. So our group is quite vast right now, and we are still growing. Many people are interested in the project, so we have many people who wants to work with us, which is really making us happy. And about the very project, we have some assumptions. So the first one is that we apply cognitive empathy to optimize the swarm behavior. The second one is that we use only LED communication. We use visual communication. And why? First of all, we don't want to have computer to centralize the or to control the swarm. We want the swarm to be autonomous, and we want each swarming agent to have their own knowledge, to have their own experience, and to have their own objectives. And we wanted to have a communication that will not be perfect. Why? Because we want to use imperfect communication the same way that evolution works. Mutation in evolution helps in adaptation, and we want to have imperfect communication in order to learn to have this kind of mutations in our knowledge base that help us in optimizing the swarm performance, and it works actually. So we have LED communication. We have LED tower with 8 segments that just show by different colors what kind of communicate, what kind of state a robot is broadcasting. We divide the behavior of robots into egoistic and empathic. Empathic behavior is when a robot decides to help another robot to make some kind of action together, or to get to a place together, or to make some kind of objective together. And egoistic behavior is when the robot just acts with its own plan of how to reach the state goal that is stated for the whole swarm. And the global goal is programmed into intuition, so into the initial knowledge of each robot. And it's the smallest amount of information that is needed for a swarm to start its learning process, to start its operation. At least the swarm has to have the goal given as a state. So we don't have goals defined as an action. So we want to get somewhere. We have the goals defined as a state. We want to get in this and this state. And then the robot learns new states and the consequences of the state by comparing the states with own knowledge. Each robot with their own knowledge, so each robot can know different things, can act in different ways, but also can share their knowledge. Yet, as the robots share the knowledge between themselves, the way the other robot will understand that knowledge can be different. And the robot reads the visual signs that are transmitted by other robots, and then decides whether to act egoistically or to act empathically, compares the possible outcomes, the predicted outcomes, with own knowledge, and based on this comparison decides which is more beneficial for it to act on their own way, or to help other robots. And the methods that we use are fuzzy states. We define the states of the robot as fuzzy numbers, and we use fuzzy similarity measures of the states that are broadcasted to the fuzzy states that are remembered in the robot's knowledge base. We have a reward system for a realized action. So if a robot decides to do something and the action will be realized, then if the action brings the robot closer to the goal, the robot gets a reward and remembers that kind of decision was connected with that kind of reward. Then we have action sequence contraction. It's technical thing connected with the notion that we can get from let's say from point A to B in many different ways, and we have to compare the state of being in point A and in being in point B, where the ways of getting there can be different. So we had to think of a way to compare this kind of getting into the state with different ways of actually getting there. Then we have state prediction, knowledge aggregation in order to omit the problem of perfect knowledge. We don't want to remember all the states because we have our resources are limited, so we have to aggregate the knowledge. And also we have neural networks to control the platform, to show the robot how exactly to perform an action, how to move their wheels, how to omit some obstacles. We use YOLO vision system because it's light and we need to make a lot of photos, a lot of pictures in order to see what states are broadcasted by other robots. And we use current control and we optimize the whole performance. And this is how our model looks like. We have an action. We have to decide if we will have a normal or egoistic behavior or artificially empathic behavior. We have to choose a particular action. We have to make the action, implement the action. Then we have to assess if the action was good or not, and then we have to change our memory. So remember the state, remember the decision and the reward, or to modify existing memory state. And we have two possible algorithm of what can happen. So first thing that can happen in our model is that a robot sees another robot and decides if it wants to help the robot or not. For example, if the second robot sees the goal because we want to get somewhere, then we can make a decision if we want to get to the other robot or not. So this part of the model is connected with making a decision about if to act egoistically or if to act empathically. After the action, we have to we call the decision, we call the intent, because we don't know the particular action that will be taken. We don't know if the robot will go straight ahead or if it will move to the side. So we say that we have an intent. We intend to go somewhere, and then we have to choose the particular actions of how to get there. And the part of the setting the intent is realized on the fuzzy numbers, and the part connected with taking a particular action is made by the neural networks and is different for every robot. And then we update the knowledge and verify if the goal was reached and if we are and if the goal is actually realized. And the second possible scenario is that a robot sees a robot that just learned something interesting and decided to go and learn from them. The learning process can take some time because broadcasting the whole sequence of how we got to a particular state of knowledge takes time. So a robot has to stop doing what it was doing, go to the other robot and to just see what is being broadcasted and learn from the broadcast. So if we want to learn, we have to stop what we do and go and talk with the other robot. Okay, I guess that I am talking a bit too long, so I will just shortly say something about this. Can I ask how much time do I have more? Sorry, but the microphone.
I'm very sorry right now. I guess that you still have time, around 10 minutes, and next we're gonna ask for some questions.
Okay.
But
Okay,
if you're tired, we can skip to the part and ask questions right now, because I'm sure there are lots of questions. Very interesting.
Okay, so maybe I will just skip the maths. I will just tell a bit about it. I will go to the photos because they are more interesting. And then if there will be questions, I guess I will get back to the maths and just show in particular what I was talking about. So what do we see here? We have the fuzzy states. I don't know if my cursor is visible. Maybe not. So we have the fuzzy states.
You can see the cursor.
Okay, so we have the fuzzy states, internal state and external fuzzy state. We have the message, the state is defined this way, and only the very agent knows what is their particular state. They can try to tell other agents what's the state, but there will be some error in the communication. As in human communication, there always is a communicative error, and so the knowledge of other robots will be altered with some of their own knowledge, because they will fill the gap in the communicate with their own knowledge, because they know what's their view of the world. So if they don't have a particular information, they will fill it with what they know, what they have in their own knowledge base. And each robot, when deciding if to act egoistically or if to act empathically, has to compare some information. So what will be the reward? So what will be the most similar to the goal? Because we give the highest reward if the intent is closest to the goal that is set for the whole swarm, and the reward will be the highest. We have to choose the highest reward from three types of decisions. So when we have our own internal state and our own external state, so information about our own internal and external state, so we know what we will get for doing an egoistic action. If we know what's the others' internal state and others' external state, but what we understand from their communicate, so how we understand their state, and how we would act if we would be in the state of other robot. So this is acting egoistically. This is how other robot will act, and this is how we would act if we would help the robot. And we have to compare these three things, and the highest reward will show us what we have to do. If the highest is for the egoistic action, we act egoistically. If the highest is for our projection in the state of other robot, then we go and help and act empathically. And if the highest reward is for the robot, for the other robot, it means that they know something interesting, and maybe it will be good to go and learn something from them. We use fuzzy similarity measures because we always compare our fuzzy knowledge with the fuzzy communicate that comes from the other robot. And if we have the similarity, we can state our intent. So intent, what we want to do. And after we have the intent, then we can send the intent to the other decision model. We have to have two. One of what will be the intent, and the second, what will be the actual set of action that will lead us to realize this intent. So then we can only send this intent to the second decision module. And now I have some photos. So this is the first photo that shows us the communication. So in the middle, we have our two robots. I will have photos with better quality in next slides. And these robots, one is signaling red, the other is signaling green. The green robot signals that it has something interesting to teach other robot. And the red signals that the robot does not yet see anything. If it would spot the green robot, it will visualize it by lighting blue colors. And on the right side, we have our LED tower. How it works? We have 8 segments. In each segment, we have 3 LED lights. And we light the LEDs so that it can be visible from all the sides of the robot. So we light it by the segments. This is our visualization of the robot, the first generation of the robot. Right now we have the third generation of the robot, but the first generation was quite big. It had 15 centimeters, and it looked like this. So it was a moving robot with 3 wheels, 2 main ones, and one for the stability. And the robots had a moving camera that was able to move 150 degrees and make photos. So we had less problem with moving whole the robot and a little bit more problem with making photos around the robot. And we simulated 3 scenarios. The antibody problem that I already described with the viruses, then the food search problem. That's the main common scenario for checking swarms of robots. So there always basic research on robot swarms is always on the problem of food search. So we have something that is hidden, and we have a swarm that has to find the hidden thing, and we also made this simulation. And the third simulation scenario that we checked was the rat and grain problem, where we have grain and we have rats. Rats have to eat the grain, and we have cats that need to not only find the rats and scare them off of the grain, but also to find the rat hole, so from where the rats are coming. And this is how our first simulative research looked like. We had to simplify the robots in order to save computing resources, because it took a lot of time to simulate egoistic behaviors. Well, now it's way better. That's the second simulation, second generation simulations. So right now we are doing simulations in a dedicated software in Unity, but also some with the students in Coppelia, but we most focus on the dedicated simulating software. Here are one of our first research with the rat problem. This is how it looked like. So we have a rat that's eating the grain, And we have robots that are the cats that are following the rat and are looking for the rat hole. But the rat ate all the grain. Okay, I guess we will skip the whole movie because it's 4 minutes long. So now I had to, oh, yes, and these are our first simulated results that showed that using artificial empathy allows us to shorten the time. Our most valued parameter was the time of reaching the goal. So using artificial empathy algorithm shortened the time by a few seconds. It was like around 3 to 5 seconds on simulation with the same other parameters in the problems, in the 3 described problems. And when we realized that our simulative research is okay, then we decided to actually build the robots. This is our first version. It had its problems, but it was, we called it ducks because it had yellow wheels, and also the camera that was moving, it made a quack quack sound when moving. So these were our ducks. And they were 15 centimeters in diameter, and they were quite heavy. Because of the LED tower, we had to put some metal in them, so they will be heavier and won't fall. And this is our swarm. We had 10 of these robots, and the cost of building one of these robots was 1,500 zlotych per one robot. Because it was the stage of prototyping, they were quite expensive. And for the safety of our robots and for the, because we wanted to make the experiments repeatable, so to be able to make the same experiments, we built an arena. It has 2.5 meter. It's 2.5 meter long and 1.5 meter vast, and it allows us for making the experiments. Also on the frame, we have a camera that is filming the experiments, and we are able to verify them. And this is our vision system. It makes 2 photos. One, on the left side, is only for the sake of the researcher, because the robots don't need this kind of image. We just want to know what the robot sees. And on the right side, the black photos with only the lights is what the robots actually see. And because the first generation had some problems, for example, the robots would stare on the wall of the arena because they saw their own reflection, like in the mirror, and were deceived that there are more robots than there actually were. So we had to make some modifications, and we created the second generation of the empathic swarm. It's smaller. It has only 7 centimeters. It has 2 PCB boards. The lower one is dedicated and created for the case of moving, for making actions, so steering the platform. And the upper one, it's actually Raspberry Pi Zero, and it's responsible for making the decision between the egoistic and empathetic action, and it's also responsible for the vision system, so for realizing what the broadcasting signals of other robots are. This is the project of the implementation. It is smaller, it works longer on the battery, also it's more resilient and more modular, and has some sensors that were lacking in our first generation. The same photo, like here we have the lower PCB board, and this is the board itself. We have two motors. We have the possibility of charging the robot by the pins. And what else? It's interesting here. Well, we still have some problems here. So right now we got a grant for making another generation of the robots, and we are in the middle of actually buying parts for the new generation of the robots. We want to have automatic charging right now, and we want to have better sensors, especially in the back on the robots. So there are still some things to change now. But the LED tower that is visible right now, everything is printed in a 3D printer. This LED tower is printed with technology that is used in reflective thingies for bikes or children, so the children are more visible at night. I don't know how it is called in English, but it was needed for us so that the lights will not mix between the segments. So we had to use this technology. It's also printed 3D, and it helps us to better show the communicated message. And also the robots have the case, outer case. It's also 3D printed. Many parts of here are 3D printed, and we are trying to make the project customizable, so we can change the shape, we can change the what's inside the robot, and create solutions for companies that want our empathic algorithm, because right now, for example, we work with an edtech company that actually will sell these robots to schools in order to teach children learning. Sorry, I'm looking for the English word. It's learning by ze wzmocnieniem. Sorry, I don't remember the word for it, but for sorry? Reinforcement learning, thank you. Yes, I forgot the word, sorry. So because the robots show the messages on the tower, students can see how the learning is happening actually real time. So it's a good tool for teaching children. And some more pictures of our robots. And this is a comparison between the first and the second generation. So it's visible how smaller the second generation is. And in the second generation, the camera is not moving. It's the whole robot that is moving, not the very camera. And the simulations in our second generation of robots, and the blue lines show that the robots see each other. And we make the same scenarios as in the first generation, but also some more. For example, we checked the possibility of teaching one robot something, for example, how to omit some obstacles, and then we made the robot teach other robots how to do it, so how to share how to share its knowledge, and so that it can teach other robots how to do something, and it worked actually. And this is some results for the food search simulation problem. And we also built a small, very small swarm of the second generation of robots. Well, the problem was the financing, so we didn't have enough money to build a huge swarm. Only 8 of these robots were built, but we have the robots divided into 2 groups because there are many people that make research on these robots. We had to divide it into small swarms of 4. But now we are building another swarm of 10, even 14 if anything won't burn. So we will be able to perform better empirical research. And the results that we have are that using artificial empathy in both simulation research and empirical research, we get a few seconds of reaching the goals faster with the same other parameters. And right now, here, yes, also some figures with the research results. And the problem at hand that we have right now this week is the problem of our robots grouping, because let's say one robot signalizes that it sees the goal, and other robots go to this robot because it saw the goal, but the robot loses the goal from its sight. But still, everybody sends the signal that there is someone that sees the goal, and we had the problem of grouping. We don't yet we don't yet know what will be the solution, because that's a really fresh problem, like from yesterday. But I wanted to show that the research is still being conducted. And the application of our research, we have an agreement. We have a commercialization with a edtech sector firm, but also we talked with other companies that want to test their own algorithm on our swarm platform. And also we are trying to make a solution for places where human cannot work, but still the empathy, like empathy in learning, is needed, for example, in warehouses or waste sorting centers. And this year and last year, we published some papers about our robots. And I guess that's all that I can tell.
Wonderful. Okay, thank you so much. Are there any questions from the floor?
Yes, there is a question from the floor. Pani Joasiu, thank you very much for your talk. I have the following question. You showed the efficiency improvement factor. Can this be related to search time? So if you had a search and rescue mission, would that mean that if you were using this empathy new methodology, would that translate directly to cutting the search time by a factor 2? You're muted. You're muted now.
Yes, sorry. If I understand the question good, yes, we are talking here about cutting the time exactly, but it's only one of the parameters that can be used. It was the easiest for us to use also, because a lot of this research is connected with students' projects. So showing it as this kind of visible parameter that can be easily interpreted by students was the most effective now. But it is this project is a kind of sandbox, because we are talking here about states, and the way we define the states and the way we define what's the quality of reaching the state. So for example, the percentage of similarity to the goal, or the time of reaching the goal, or the closeness to the goal, even in the geographical sense. Yes, the parameters are for us to choose. Yes, these were the easiest one for us right now at the beginning of our project to choose. I don't know if I answered the question well.
Yeah, that sounds good. I have one more. If we double the number of robots in a swarm, would that linearly translate to the efficiency? So we
I don't know.
How would that work?
I don't know if it would be a linear relation, but the more the robots in the swarm, the more possibilities for empathy, because there are the more just moments where the robots just see the broadcast signals. So the more the possible places to apply the empathy. So yes, I don't know if it would be a linear, but yes, the number of because we don't have always the meeting of 2 robots, we have the meeting of more robots also, but yes, it will be there are more possibilities for empathy. And we had this kind of problem because in the first generation of robots we had 10 of robots, and our arena 2.5 meters by 1.5 meters was okay. But in the second generation, when we only had 4 robots for one experiment, the arena was too large because the robots just didn't meet themselves in this arena. So we had to shorten the arena for the empathy to be even possible. So yes, with more robots, there is the optimization and more place for the empathy and for better results.
Right. Thank you very much. And there is one question from Fatina Basmanji from CBK-PAN. So thank you for the very interesting lecture. I have one question. What is the key difference between the artificial empathy and multi-agent reinforcement learning in the reward function in reinforcement learning in design in such a way that it considers, for example, the punishment for the egoistic action and a reward for helping action? Quite difficult.
If I understand the question well, our system implements the reinforcement learning. Yes, the decisions that were rewarded with a good reward are just remembered. But where is the artificial empathy, and why this is not the collaboration but artificial empathy? It is in the knowledge of each robot and in the possibility of each robot to predict. The collaboration is now. I see, I react. And artificial empathy is I know, so I predict, and I choose my reaction. So in the future, my reaction for the action that will happen or will not happen will allow me for collaboration. Artificial empathy makes a place for collaboration, for better collaboration, and reinforcement learning is the reward for the collaboration. So the only difference is in time and in predicting, and that in the empathy, we are thinking a few steps ahead. We are making strategies and we are not reacting right now. Okay.
Thank you. Was written by Fatina. Okay, so are there any more questions? Well, I guess you said it all during your lecture. So, Dr. Joanna, thank you so much for everything you showed us. We crossed our fingers for your luck. All those research seems to be very impressive and quite cutting edge. So I hope we're gonna see some more of it later in perhaps next year somewhat, but we cross your fingers for your luck. Thank you so much.
Thank you very much.
Okay, thank you all so much. We'll see each other in 2 weeks, I suppose.
That's right. We will be announcing our seminars. Pani Jasiu, thank you very much.
Thank you.